Okay, so hi class, we're continuing with the day 49 assignment. It's got a lot of problems on Hess's law and enthalpies of formation, and we did a few of each of those. Now we're going to do a combination of the two and see how they compare. So we're going to start off with this one, 2NO plus O2 gives you 2NO2 gas. We're going to try to find the heat of reaction for that. So we have a couple of equations down here. And we're going to use those to try to recreate this equation up here. So since these are already written here, I'm going to go ahead and I think I have enough space to work on this sheet, so I'm going to do that. You should probably choose to either work on line paper or not. If you work on the sheet and then put something on line paper, please reference on the sheet that it's on line paper, so I don't think it's just left blank. Okay, so we're going to call this equation 1, and this is going to be equation 2. So what we see up here is we need to have NO, nitric oxide, on the left-hand side of the arrow. Again, I'm going to circle the arrows the way I like to do it. Okay, so we're going to have NO on the left-hand side. And if we look down here, we see the only place NO appears is in this first equation on the right-hand side. So we know we're going to have to reverse that. So I'm going to go ahead and label this equation 1A. And I'm going to draw an arrow down to it. Again, that's at your discretion to do that, but I just find it helps to keep me organized. And now we're going to reverse this and make it 2NO and then the arrow, and then everything on the reactant side goes over to the product side. There we go, and then we take the enthalpy. And you'll notice this is different than the enthalpies that we've had in previous problems. These are positive numbers, so enthalpies are not always negative numbers. They can be positive. We'll talk about why sometimes they are and why sometimes they aren't. That'll come later on in the course. So anyway, we're going to take the delta H, and we are going to make it negative 180.6 kilojoules. And then the last thing I'm going to do is lightly put a line through that so I don't mistakenly use it again. Okay, so we have 2NO on the left-hand side of the arrow, and we have the same thing up there. On the right-hand side, on the left-hand side up here, we have an O2. So if we look down here, we have a 2O2 on the left-hand side of this arrow, but on the right-hand side of this arrow, we have an O2. So since they're on opposite sides of the arrow, it's going to be a subtraction. So you have 2O2 minus 1O2 will give you 1O2, and it will appear on the side where the larger of the two numbers was, this side right here. So this is going to cancel out altogether, and this 2 is going to cancel out. We'll just X out the 2. So it's going to be 1O2, and that matches up with what we have up here. And finally, the other thing we have is N2 gas right here on the left-hand side of this arrow, and N2 gas here on the right-hand side, so those two are going to cancel out. And the only thing left after all this is the 2NO2 on the right-hand side of the arrow, which matches up with this. So we have 2NO on the left, we have O2 on the left, and we have 2NO2 on the left. So we've got everything in place. Remember, if you reverse an equation, you change the sign on the enthalpy. If you multiply through by a factor, by a 2 or a 3, you do the same thing to the enthalpy. But when you do these additions or cancellations, that does not change the enthalpy. So now we're ready to go ahead and do an addition of 66 plus negative 180.6. And that is going to give us negative 114. So the delta H of that reaction is going to equal negative 114.2 kilojoules. Okay? And that takes care of that. All right. Now, let's go ahead and figure out the delta H of reaction using the enthalpy of formation method. So again, all we need for that is just the original equation up here. And so we have the enthalpies of the products minus the enthalpies of the reactants there. So I'm going to write the formula again. So it's sigma n delta H of formation of products minus sigma n delta H formation of reactants. Okay, simple enough. So let's go to our purple sheet. And of course the n means we multiply by the coefficient. So let's go to our purple sheet and find NO2. And we have NO2 here somewhere, I believe. Well, maybe not. So what do you do if you don't see it there? I just want to be sure I'm not missing it here. I don't see NO2. Well, one other place I'm going to look is I'm going to look at the front page and see if it happened to be one of the ones we did there. And I don't see it. So what do we do? So here's what I do. I go to my book. There it is, big old book. And I'm going to turn to Appendix C. And if that doesn't have it, then it probably doesn't exist. But that has lots of stuff. So Appendix C. And let me find it, and then I'll zero in on it for you here. Okay. And there it is, 33.84. Let me get that again. I almost lost that. Sorry. Try that again. Okay, let's go to the book and see if we can find it in there somewhere. So it's in Appendix C. I mentioned that on one of the earlier, somewhere either in the notes or one of the assignments. So we look for NO2. I'm going to adjust the camera here. And there it is right there. And it is 33.84. So that's the enthalpy of formation of nitric dioxide. Okay, so that's the, okay, so here we go. I went to the textbook. I found it in the textbook. There's NO2, and there's the enthalpy of formation of 33.84. So that's the number we need. So I'm going to put the textbook away. Now let's take a look up above real quick. You notice that up here in this equation, it has a number, delta H, of 66.4. But that's for 2 moles of NO2. You'll notice this is the enthalpy of formation reaction. N2 plus 2 O2s is 2 NO2s, except you have to divide everything through by a half, because for the enthalpy of formation, it's only supposed to be 1 mole of the product. Here we have 2 moles. That's why this number is twice the number that I just said of 33. Okay, so here we go. So we have 2 times 33.84 on the product side, and now we're going to subtract from that the sum of the reactants. So it's going to be 2 times, and again I'll go and see if my purple sheet has NO, and it does not. So I'm going to go back to the book, bring it on back over here, and there's NO right there, and it's 90.37. Notice that these are both positive numbers, so it's going to be 2 times 90.37. And I forgot to put my big blocks around. I always do that because you're going to need parentheses inside of those. So there's a block, and then it's going to be minus the enthalpy of formation of oxygen, but we've said this several times now. The enthalpy of formation of a pure element is 0. It's just simply defined as 0. So there we go. And so there that is. So now we're going to do the math, and it's going to be 2 times 33.84. And then you're going to subtract from that 2 times 90.37. And what that gives us is negative 113.1 kilojoules. Okay, and you'll notice this number is pretty darn close to this one. Why is there any difference at all? Well, you'll notice that this number was not exactly half of this number right here, and this number is not exactly half of this number. Because remember, these numbers were for 2 moles, and these numbers are for 1 mole. So I rounded differently, so they ended up a little different. But effectively, you got the same answer using both methods. So what is the enthalpy heat of formation of any pure element in its standard state? So the enthalpy, and you can just use symbols if you know them by now, delta H of F is 0 for pure elements. Okay? And that takes care of that. All right, let's keep going. Let's move to number 17. And let's see. Actually, this is what we just did. Okay? So we don't need to do this. That was actually a duplicate I meant to omit. So there we go. So that's the same thing we did right there. That saves us a little time. So how do the answers for the enthalpy of formation of Hess's law compare? They are the same. If we neglect that rounding error, they are the same. They should be the same. You're figuring out the same thing. How much heat is going into or out of that chemical reaction. And that's what the purpose of both of these is. That's the purpose of calorimetry as well. How much heat is going into or out of a chemical reaction. Do another combination of the Hess's method and enthalpy of formation method and see how they compare. So what we're going to do is we have a combustion reaction for methane. So it has the usual components of a combustion reaction. It has oxygen, and then on the product side it has carbon dioxide and water, and you can also see it's already balanced for us. So what we're going to do down here is, first of all, I want to add a state here, a gas. So you can see that we have 4 reactions, and you'll notice they're all formation reactions. They're all producing 1 mole of each of these compounds from their most basic elements. Typically for this, though, we don't count the O's here. It's just thought that O2 exists as that. It's not really created from O plus O. So and it has an enthalpy of formation of 0. So we basically get rid of these, and that just is an O2. It's just the way oxygen is. So it really doesn't have a reactant side. It just has that product there. Okay, so we're going to go ahead and do this, and I'm going to go ahead and label these reactions over here 1, 2, 3, and 4. And let's see how we can arrange these to look like this equation up here. So we see the first one has CH4 on the right-hand side of the arrow. Then I'm going to circle the arrows the way I like to do it. So CH4 is on the right side of the arrow. Up here in the target reaction, the one we're trying to match, it's on the left-hand side. So that means you're going to have to reverse number 1. So I'm going to bring it down here. I'm going to call this 1A. And we're going to reverse it around so CH4 is on the left. There we go. And since we reversed it, we have to take its enthalpy and we have to change that to a positive. These should all be, say, delta H's in front of it. Okay, so that takes care of 1. I'm going to go ahead and lightly put a line through this so I don't use it again. Alright, the next one we just have O2. We're going to leave that. Carbon dioxide does appear on the right-hand side here, and it appears on the right-hand side there, so we're not going to change equation 3. Equation 4 has water on the right-hand side and on the right-hand side here. But you can see there are 2 moles of water and only 1 here. So this is an equation where I'm just going to do something you're not supposed to do in math. I'm going to put 2 here, and I'm going to put a parenthesis around everything here. Right there. So the 2 is going to multiply to that, to that, to that, and to the enthalpy as well. So I'm going to come down here, and that's going to be my equation 4a. And it's going to be 2H2 plus 2O2, that's what gas is. And that's going to give us 2H2O. And it's going to double this number right here. And that's going to give us, I believe, negative 483.6. Those are all kilojoules per mole. Okay, so let's see how things now cancel out. So we still have these 2 reactions here. Well, I'm going to put a line lightly through this reaction. Okay, so we have CH4 here and CH4 here. That's good. And again, I want to circle my arrows so I'm clear where I am. We have 2H2 on this side, on the left side of this arrow in 4A, and in 1A we have 2H2 on the right side, so those 2 are going to cancel out. We do have 2H2O on the right side of the arrow, and we have that up here, so that's good. We have CO2 here and here. Okay, if we come up to this equation for oxygen, we have an oxygen on the right there and 1 on the left there, so those cancel out. But we still have 2 O2 left down here, and we have 2 O2 up there. So everything does match up. So the equations we're interested in adding are 2, which is just 0, 3, 1A, and 4A. Those are the ones we're going to add, so let's go ahead and do that. So we start with negative 393.5. And we're going to add to that 74.8. And we're going to subtract from that 483.6. And it gives us negative a delta H of reaction for methane of negative 802.3 kilojoules. And since we've reacted exactly 1 mole, we can call that kilojoules per mole if we want to do that. So that would be our reaction there. Okay, so I went ahead and did the enthalpy of formation here already. So there's the formula. You've written it a few times before. So we're starting with products, which is carbon dioxide. That number is going to be negative 393.5 right there. And then we have 2 moles of water. The number for water is negative 241.8. We put it right there and multiply it by 2 and block that off. And then we're going to subtract the delta H of the reactants. So for methane itself, it's negative 74.8. There it is right there. Only 1 mole of that. For oxygen, we have 2 moles, but oxygen is a pure element, so it has no enthalpy of formation, and therefore we have a 0 there. And if we do the math on this equation right here, we end up with negative 802.3, which is the same number we ended up with using Hess's law. So they should give you the same numbers. They're both computing the same thing. Okay, so now we're going to do the same thing for butane. That's the kind of gas that was in the lighters that you were lighting the other day back in the lab. And so what we're going to do is write a balanced chemical reaction first. So this is a combustion reaction, so it's C4H10 plus O2, and that's going to give us CO2 plus H2O. Okay, and these are all going to be gases. We'll assume the H2O is going to be a gas as well. Or, excuse me, going to be well, it says gas up here, so we're going to go with that. Okay, so we have the enthalpies of formation here, but what we don't have is the balanced chemical equation, so let's do that. So you don't want to balance oxygen. It's a pure element, and it appears in two locations on the right. So let's start with either carbon or hydrogen, and we're going to go ahead and start with carbon. We have 4 carbons on this side and 1 on this side, so we're going to put a 4 up here. Okay. Now, the 4 balances or affects the carbon, also affects the oxygen, but we want to stay away from oxygen until the very end, so we're going to move on over to hydrogen. We have 10 on this side and 2 on this side. That means we need 5 there. Okay, and what we will do then is we have 5 hydrogen. So now for oxygen, we have 5 O's there and 8 O's there. So that means we're going to need to have 13 halves here. Why? Because 8 there and 5 there is 13, and 2 times 13 halves is going to be 13. So that makes the oxygens balanced. Now, normally we would multiply through by 2 to get rid of that denominator 2, so it would be 2, 13, 8, 10. That gets rid of that. But we're just as interested here in having a molar number, a number for a single mole of butane. So we're going to go ahead and leave the 13 halves there. We've got a calculator. It's not that hard to deal with the fraction. So let's go ahead and deal with the fraction. Actually, as soon as I said that, I realized, why are you not going to have to deal with the fraction? Because it's with oxygen, and oxygen is going to be 0. So it doesn't really matter that you have a fraction there or not. But if you did have to do a fraction, it's not a big deal. Okay, so let's go ahead and do this. So it's going to be, and I'm not going to write the equation, I just want to get you through this. So it's going to be CO2, we have right there, and we have 4 moles of it, so 4 moles of CO2 times negative 393.5 plus, we have H2O, and we have 5 moles of H2O, so we're dealing with a lot of moles here in this thing, negative 285.8, and we close that. That takes care of the products. Then you're going to subtract the reactants, and the reactants for butane, you only have 1 mole of it, so it's just simply negative 125.6, and of course oxygen is going to be 0, so we can close that up and go ahead and compute. Okay, and we get negative 3003. And over here, it's going to be a negative, that's going to be a plus 125.6. Alright, and so it's going to be negative 3003 plus 25.6. And that's going to equal negative 2877.4 kilojoules. And since it is of just 1 mole of butane, we can write kilojoules per mole. Okay, and that's our delta H of reaction. It's also our molar delta H as well. All right. Okay, so I skipped a few problems here. I'm also going to skip 23 right here. So let's move on to this one with ethane. And so we're going to use Hess's law by writing the equations of formation for each of these compounds. So let's get started on that. So number 1 is going to be 2 carbons in the graphite form, solid, plus I'm going to need 3 H2 molecules, which are in gas form. And that's going to give me 1 mole. Everything has got to be for 1 mole of whatever the compound is that's being formed. That's the rules for enthalpy of formation. Okay, and so the delta H of that is going to equal, you can grab your purple sheet. And ethane is negative 84.68. It was also on the front page because it was one of the ones we did on the front, 84.68 kilojoules. Then you could put per mole because it is for 1 mole of that. Okay, 2. It's oxygen. O2. It's basically just there. It has 0 delta H of 0. It really doesn't factor into the equations. This one doesn't. There will be other oxygens that do, so we're going to leave that. 3 is carbon dioxide, and so that's going to be a C plus an O2. This is again in graphite solid form, and this is gas. And this is going to give you CO2 and gas. And we've used this one quite a bit. Delta H equals negative 393.5. And finally, number 4 is for water, and it's in the liquid form. Be sure you see that. So it's H2. And we want 1 mole of water, which means we have to have half a water molecule. It's the only time in chemistry that you'll see fractions as coefficients. At least to my knowledge it is. So it's H2O because we need exactly 1 mole of that. And it is in liquid form, so I'm going to put an L there. This is gas and gas. And so the enthalpy in liquid form is negative 285.8. Okay, so let's start arranging these. I like to circle the arrows so I'm clear which side is which. So on the right side of this equation we have C2H6, but it needs to be on the left side of our target equation. So I'm going to come down here and I'm going to reverse it. And we're going to call this 1A. More normally here, C2H6. Okay, and then the reactants go to the other side. And what that means is that this number reverses to a positive number. Okay, so good. We got this over on this side. O2, we really don't even have to think about. It's for this O2 at least. Now CO2, it's on this side, and we have it here on this side. One thing I didn't do though, and this was terrible of me not to do this, you have to balance the equation. You can't do anything in chemistry without a balanced equation. About the only thing you could do is determine solubility of compounds without balancing the equation, but you really do need to balance the equation. So let's do this. So we have 2 carbons here and 1 here, so we're going to put a 2 here. Okay, we want to stay away from balancing oxygen till the end for 2 reasons. It appears as a lone element there, so leave it alone until the end. And it appears in 2 different locations on the right side of the equation, so leave it alone for that reason as well. So let's go on to hydrogen. We have 6 hydrogens on this side and 2 on this side, so I need to multiply this by 3. So my hydrogens and carbons are in balance. So now let's see what goes on with oxygen. We have 2 times 2 is 4, and 3 times 1 is 3. So that's 4 plus 3 is 7. So the way to get this to balance, we need 7 on the other side. So we put a 7 over 2 here. Because 2 times 7 halves is going to give you 7. And that's what you need. You need 7 moles on that side. So our coefficients are 1, 7 halves, 2, and 3. We're not going to worry about that. Normally we would go through and iron that out and multiply everything by 2. So this would be 2, 7, 4, 6. That would get rid of the 2 in the denominator. We're not going to worry about that right now. You don't really need to. So let's just not do that. So that didn't affect our first operation here from 1 to 1A because C2H6 is just 1 mole. So we don't need to change anything about that. Okay, so now I skipped the oxygen here, and let's go to this carbon dioxide. And so here's the situation. We have carbon dioxide here, but we need to have 2 of them for the equation. So what I'm going to do, you shouldn't do this in math, but I'm going to just do it take a little liberty here. I'm going to put a parenthesis around everything on that line, including the enthalpy. And I'm going to multiply that by 2. And now I'm going to take this equation, bring it down here, and this is where we're going to actually do that. I'm going to call that 3A. So we have 2 times C solid, carbon solid, plus 2 times O2, and that's gas. And that's going to give us 2 CO2, gas. And what's that going to do to the enthalpy? We're going to have to multiply the negative 393.5 by 2, because we're multiplying everything by 2. And that gives us negative 786, or let's just call it negative 787. Actually should have been negative 787. I don't know how I got that answer. Oh, I punched in the wrong number. Anyway, it is 787. Okay, so that takes care of that. Now, how about the water here? Okay, so we have the water on the correct side. It's on the right side of the arrow, and up here it's on the right side of the arrow. But we need 3 of them. So we're going to, by the way, I'm going to put a line through this because I don't need this equation anymore. I don't need this one, and I don't need this one up here. We've already swapped that around. So now we're down to water, and I'm going to multiply that by 3. I'm going to put a big parenthesis around everything there. And then this is going to come down here. We're getting a lot of arrows lined up here. 4A. So it's going to be 3 times H2. 3 times 1/2 O2. So 3 times 1/2 is 3/2. That's a gas. And finally, that's going to give us 3H2O. And that's going to be a liquid. This one we said was going to be a liquid. And the delta H, so it's going to be 3 times negative 285.8. And that's going to give us negative 857.4. Okay, so before we add anything, let's see if our equations work out. By the way, last thing I want to do is put a line through this because I'm done with that equation right there. I just don't want to accidentally add those numbers in or start playing around with those. So let's see where we are. We have C2H6 on the left of this arrow, and it's on the left of this arrow. We have 2C here on the right of this arrow, and we have it over here on the left of this arrow. So they're on opposite sides of the arrow, so they're just going to cancel out. All right, how about H2? Over on the right-hand side of this arrow, we have 3H2, and over on the left-hand side of this arrow, we have 3H2. So those two are going to cancel out. Okay, now how about O2? We have 2 O2 plus 3/2 O2. So let's do a little fraction math here. 2 is equal to 4 over 2. Okay, I can change 2 into 4 over 2 plus 3 over 2 is going to equal 7 over 2. And that's exactly the coefficient that we need up here, 7/2. So when you add these two together, they work out. They get added together because they're on the same side of the arrow. So that works out fine. The 2 CO2 is on the right side of the arrow, and the 3H2O, right side of the arrow, right side of the arrow. So everything lines up. We have this plus 7/2 O2 plus 2 CO2 on the other side, on the product side, plus 3H2O also on the product side. Okay, so now we're ready to add up these numbers right here, and that will give us the enthalpy of reaction for 1 mole of ethane. So it's going to be 84.68 minus 787 minus 857.4, and that gives us negative 59, or let's round it to 60, negative 1560 kilojoules, and since it's for 1 mole, we can say per mole. Okay, and there's the answer to that one, okay? Now we're going to do the same thing using the enthalpy of formation. One last time I'm going to write the equation. So the delta H of the reaction, for this reaction up here, is going to equal the sums and differences of the enthalpies of formation of each of these compounds. So that's going to equal the summation times the number of moles of delta H of formation of the products. I really urge you to write these equations out every time. As tedious as it may seem, it'll pay off in the long run. Delta H of formation of reactants. Okay, so let's go ahead and get started. So we have 2 CO2, so we're going to start with our big block there, 2, and that's negative 393.5, plus we have 3 H2Os, 3 times, and it's in liquid form, so it's 3 times negative 285.8. We're going to close that up. This is for the products. Now we go to the reactant side. We subtract that out, this part over here, and we have C2H6, and the enthalpy of formation for that is, that in a block, negative 84.68, plus for the oxygen is 0, so that's a 0, and so now we're ready to compute. Again, I like to do this first, this second. Don't like to do too many things on the calculator at the same time. And that gives us negative 1644.4. And then over here it's minus a negative, so it's going to be plus 84.68. And so the delta H, and I'm off screen. Gosh darn it, sorry I was off screen for that whole thing. Anyway, why don't you take a second and look at that, where I got those numbers. Let me just say them again. So we have the delta H of CO2, and we had it up there, right there, before we crossed it out. It's on the front of your sheet anyway, on the front page. And we have 2 moles of that. Then we have 3 moles of water, so it's 3 times, and there's the delta H for water. It's negative 285. Again, it's on the front page. And then you subtract from that the delta H of the reactants. And so the reactant, the only one that's there is this one. The oxygen is a 0, so that's going to be negative 84.68, and you subtract that, it becomes plus 84.68, and we add that in, and we get the same number. Okay, and that's your answer for that. Okay, and I'm going to skip 24. Okay, let's just skip it. We've got enough problems for this weekend. So that's going to wrap it. We're at an hour. I think that's enough. And remember, you have a quiz on Monday on the 60 ions, so we want to keep working on those, and we've been working on those for a long time. Keep doing that, and we will do some more problems on Hess's law, enthalpy, what we've done here. Come in, try to have this understood walking in the door. We're also going to do bond energies, and then we're going to move away from thermochemistry in the next day or so. So the class moves very fast, and it's just the way we have to do it. So come in as ready as you can be on Monday, and we'll go from there. So have a nice weekend, and we'll see you on Monday.